Imagine a time before time existed, a place where the very concepts of space and emptiness were meaningless. This was our universe in its infancy, an infinitesimal point containing all the energy of the cosmos, compressed into an unimaginable singularity. Then, in a flash of unimaginable brilliance, the Big Bang occurred. This wasn't an explosion in the traditional sense, but rather a rapid expansion, an outward surge of energy so profound that it continues to shape the universe we know today. From this point onward, our universe was no longer static, no longer a point of infinite density. It began to cool and expand, a process that continues even as you read these words. As the universe expanded, energy transformed, giving rise to the fundamental forces of nature and the building blocks of matter. This was the beginning of everything, the birth of the cosmos from a point of pure potentiality. In the first fleeting fractions of a second after the Big Bang, the universe was an inferno, a roiling sea of energy where temperatures soared beyond our ability to comprehend. During this epoch, the universe was dominated by radiation, a chaotic soup of particles and antiparticles constantly colliding and annihilating each other. Time itself seemed to operate differently, governed by the strange rules of quantum mechanics. But as the universe expanded, it also cooled. This cooling was crucial, as it allowed for the separation of the fundamental forces that govern the universe. Gravity, the strong force, the weak force, and electromagnetism. With each passing moment, the universe became a more stable, more hospitable place for the formation of matter as we know it. As the universe cooled further, it crossed a critical threshold, a temperature at which energy could begin to condense into matter. This wasn't a sudden transition, but a gradual process, like dew forming on grass as the night grows colder. Out of the cooling energy bath emerged quarks, the fundamental building blocks of protons and neutrons. The universe was still young, less than a second old, but it was already beginning to take on a familiar structure. Around 10 to the negative 36 seconds after the Big Bang, the universe underwent a period of exponential expansion known as inflation. Imagine a balloon suddenly inflating to thousands of times its original size in a fraction of a second. That's inflation, a brief but crucial period that stretched the fabric of space-time faster than the speed of light. Inflation helps to explain some of the most puzzling features of our universe, such as its remarkable uniformity. Remember those tiny density fluctuations we talked about? Inflation took these quantum-level variations and stretched them across vast distances, creating the seeds for the large-scale structures we observe today. Without inflation, the universe would have been a very different place, perhaps too uniform to support the formation of galaxies, stars, and ultimately, life itself. Inflation smoothed out the early universe, ironing out any wrinkles or irregularities, while simultaneously sowing the seeds for the cosmic structures we see around us. This rapid expansion set the stage for the next phase in the universe's evolution, the formation of the first elements. As the universe continued to expand and cool, a crucial event occurred, the formation of the first atoms. Before this point, the universe was still too hot for electrons to bind to atomic nuclei. Protons and neutrons, the building blocks of atoms, existed, but they were constantly bombarded by high-energy photons, preventing them from forming stable atoms. However, as the universe cooled to around 3000 degrees Kelvin, a pivotal transition occurred. Electrons, no longer possessing enough energy to resist the pull of atomic nuclei, began to be captured, forming the first stable atoms of hydrogen. This event, known as recombination, marked a profound change in the universe. The constant scattering of light by free electrons ceased, and the universe became transparent. With the formation of neutral hydrogen atoms, the universe was bathed in light, a faint afterglow of the Big Bang that has been traveling through the cosmos ever since. This afterglow, known as the cosmic microwave background radiation, provides us with a snapshot of the universe as it was just 380,000 years after the Big Bang. It's a treasure trove of information about the early universe, a cosmic time capsule that allows us to study the conditions present when the universe was in its infancy. The formation of hydrogen atoms was a pivotal moment in the universe's history, but it was just the beginning of the story. The universe was still young, still evolving, and the stage was set for the creation of heavier elements. Remember those tiny density fluctuations that inflation stretched across the cosmos? These regions of slightly higher density, now populated by neutral hydrogen, began to coalesce under the relentless pull of gravity. These clumps of hydrogen gas, drawn together by gravity, began to heat up and spin. As more and more hydrogen gas accumulated, the temperature and pressure at the center of these collapsing clouds increased dramatically. Eventually, the temperature and pressure became so great that nuclear fusion ignited, fusing hydrogen atoms together to form helium, the second lightest element on the periodic table. The birth of these first stars marked a turning point in the evolution of the universe. Stars are the cosmic furnaces where heavier elements are forged, elements like carbon, oxygen, and nitrogen, which are essential for life as we know it. Through a process called stellar nucleosynthesis, stars fuse lighter elements into heavier ones, releasing enormous amounts of energy in the process. This energy not only powers the stars but also illuminates the universe, providing the light and warmth necessary for life to emerge. The early universe, dominated by radiation and the formation of the first elements, was a hot and chaotic place. But as the universe continued to expand, it also continued to cool. This cooling was crucial, for it allowed for the formation of more complex structures, including the first molecules. In the searing heat of the early universe, atoms were constantly colliding with each other at incredibly high speeds. These collisions were too violent for any lasting bonds to form. However, as the universe cooled, the speed of these atomic collisions decreased. Eventually, the collisions became gentle enough to allow for the delicate dance of chemical bonding to begin. Atoms, no longer content to exist in isolation, began to pair up, sharing their electrons to form the first molecules. This marked a profound shift in the universe's evolution. The formation of molecules heralded the dawn of chemistry, the science of how atoms combine to create the incredible diversity of matter we see around us. From the air we breathe to the water we drink, from the proteins in our bodies to the silicon in our computers, everything we experience is made possible by the magic of chemical bonding. In the vast expanse of the early universe, within the swirling clouds of cooling gas, a remarkable event occurred: the formation of the first molecule, helium hydride. Helium hydride, a simple molecule consisting of one helium atom and one hydrogen atom, might seem like an unremarkable character in the grand cosmic drama. However, its formation marked a pivotal moment in the universe's history, the moment when chemistry took its first tentative steps. Helium, being the second most abundant element in the universe after hydrogen, was readily available in the early universe. Hydrogen, the most abundant element, was everywhere. As these two elements collided in the cooling gas clouds, a special kind of bond formed, a bond that would change the course of cosmic history. Helium hydride might seem like an unlikely candidate for the first molecule. Helium, after all, is a noble gas, known for its reluctance to bond with other elements. However, in the extreme conditions of the early universe, even helium could be coaxed into forming a bond. This simple molecule, born from the cooling remnants of the Big Bang, paved the way for the formation of more complex molecules. Molecules that would eventually give rise to stars, planets, and ultimately life itself. The formation of helium hydride wasn't just a singular event, it was the start of something much bigger. This simple molecule, once formed, acted as a catalyst, facilitating the formation of other molecules. Like a cosmic matchmaker, helium hydride brought atoms together, allowing them to overcome their mutual repulsion and form more complex structures. As more and more molecules formed, the universe began to transform. What was once a uniform sea of atoms was now becoming a complex chemical soup, a breeding ground for the building blocks of life. Over eons, these molecules would clump together, forming dust grains, asteroids, and eventually, planets. The legacy of helium hydride can be seen in every aspect of the universe we observe today. The stars that light up our night sky, the planets that orbit them, and the very molecules that make up our bodies are all connected to that first simple molecule. We are, in a very real sense, the descendants of those early cosmic reactions, the products of billions of years of cosmic evolution. The birth and evolution of the universe might seem like a distant, abstract concept, something confined to textbooks and scientific journals. However, the echoes of those early events resonate within each of us, woven into the very fabric of our being. Every atom in our bodies, every element that comprises the world around us, was forged in the heart of a star or in the crucible of the Big Bang. The carbon in our DNA, the oxygen we breathe, the calcium in our bones, all were created billions of years ago in the nuclear furnaces of stars. We are literally made of star stuff, connected to the cosmos through an unbroken chain of cosmic events stretching back to the Big Bang. The next time you gaze up at the night sky, remember that you are looking back in time, witnessing the light from stars that died millions, even billions of years ago. The universe is not a static, unchanging backdrop, but a dynamic, ever-evolving entity, and we are an integral part of its ongoing story. The journey from the Big Bang to the first molecule is a testament to the interconnectedness of the cosmos, a tale of how the universe evolved from a state of unimaginable simplicity to the complexity we observe today. It is a story of cosmic evolution, of how energy transformed into matter, how atoms assembled into molecules, and how those molecules eventually gave rise to stars, planets, and life itself. As we continue to explore the universe, both through our telescopes and through the microscopes that allow us to peer into the quantum realm, we gain a deeper appreciation for our place in the grand cosmic scheme. We are not separate from the universe, but rather an integral part of it, woven into its very fabric. The story of the first molecule is ultimately our story, a story that began billions of years ago in the fiery crucible of the Big Bang and continues to unfold to this day. It is a story that should fill us with wonder and a sense of profound connection to the cosmos. A story that reminds us that we are all children of the stars, born from the same cosmic dust that gave rise to everything we see around us.